Hello, everyone, and welcome to this final capstone explainer for your software engineering program. First off, a massive, massive congratulations to you for making it this far. You've worked incredibly hard to get here. Today, we're going to consolidate everything you've learned. You see, what you really must realize at this stage is that mastering database systems is not just about learning how to write clever SQL queries. It's actually about understanding the professional vocabulary that software architects use to design massive, distributed, and fault-tolerant information systems. Knowing these concepts inside and out, well, that is exactly what separates a beginner from a true professional. So let's take a step back, look at the big picture, and tie all these crucial architectural principles together.
Here's a quick look at our syllabus for this final review session. We'll be covering database systems and models, relational concepts and normalization, database design and transactions, analytics, big data and cloud, database administration, and then we'll wrap it all up with a capstone summary and themes.
All right, let's jump right into Section 1, Database Systems and Models. Before a single line of code is ever written, we really have to transition from a chaotic world of raw data into structured, logical models. The absolute core building blocks of this modeling are entities. Think of an entity as simply anything you want to collect data about, like a customer, an agent, or maybe a product. Now, these entities are described by attributes. Attributes are just the characteristics of that entity, like a customer's name or their phone number. And finally, relationships describe the associations among these entities. For example, a one-to-many relationship where one single agent serves many customers. The biggest takeaway here is that when we eventually move to implementation, these logical entities map directly to our relational tables, and those attributes, they become our columns.
Now, to make that transition from logical model to physical table smooth, we absolutely must use strict naming conventions. For instance, attributes should use clear prefixes or suffixes, like underscore code, to instantly tell another developer exactly what that data is. Entities should be singular nouns representing a single subject, and relationships should use active or passive verbs. Following these rules isn't just about making things look neat and tidy. It's actually essential for translating complex business rules into logical models without any confusion. It ensures that when someone else comes along and reads your design, the architecture literally speaks for itself. Okay, that wraps up our first topic on models. Let's look at how we link them together.
Section 2, Relational Concepts and Normalization. Moving chronologically into the relational engine, this is where our abstract data models are transformed into rigorous linked tables. The absolutely crucial point here is understanding the different jobs our keys perform. A primary key enforces what we call entity integrity. Its job is to uniquely identify every single row in a table, and to do that job, it absolutely cannot contain any nulls, which, as a reminder, are missing or unknown values. A foreign key, on the other hand, enforces referential integrity. This is simply a primary key from one table that's been placed into another table to link them together. Every foreign key value must either be null or perfectly match an existing primary key value in the related table. This kind of controlled redundancy is exactly how relational tables relate to one another. We also have secondary keys, but those are used strictly for data retrieval purposes. But listen, simply linking tables together isn't enough. They have to be structured correctly. Normalization is the process we use to assign attributes to entities to eliminate unnecessary data redundancies. I literally cannot emphasize this enough. Bad design and data anomalies simply cannot be fixed by good coding later on. No way. If your database contains uncontrolled redundancies, your application will eventually suffer from update, insertion, or deletion anomalies. And that's true no matter how elegant your software engineering is. So we achieve this structural perfection through the normalization process, which we do in specific stages. We start by moving to first normal form, ensuring we have proper tables with no repeating groups. Simple enough. Then we move to second normal form, and finally to third normal form, which ensures there are no transitive dependencies. Basically, that just means non-key attributes aren't determining other non-key attributes. By identifying these functional dependencies, we reach at least 3NF, guaranteeing a solid, anomaly-free foundation. All right, that covers the relational engine. Now, how do we actually build and run these databases out there in the real world?
Let's dive into Section 3, Database Design and Transactions.
Let's look at the life cycle of database creation and those critical mechanisms that protect our data when thousands of users access it simultaneously. Because databases don't just magically appear, right? They follow the database life cycle, or DBLC. This involves 6 phases, starting with an initial study and design, moving through implementation and loading, into testing, operation, and finally maintenance and evolution. The key word you need to remember here is iterative. It's an ongoing process of creation, enhancement, and eventual replacement that sits right within the broader systems development lifecycle of your entire software project. Once your database is operational, you're going to face the chaos of concurrency. That's multiple users trying to update the exact same data at the exact same time. If this isn't managed, it leads to a deadlock. Imagine transaction 1 locks data X and needs data Y, while transaction 2 locks data Y and needs data X. They're just going to wait for each other forever. This is often referred to as a deadly embrace. To prevent complete system gridlock, your database architecture requires strict concurrency control mechanisms. The architectural solution to guarantee what we call serializability, meaning concurrent transactions yield the exact same result as if they were executed one after the other, is the two-phase locking protocol, or 2PL. Let's see how this builds. First, in the growing phase, a transaction gathers all the locks it needs without unlocking anything. Once it has them all, it hits the locked point, and only then is the data actually modified. Finally, in the shrinking phase, it releases the locks and it cannot ask for any new ones. Now, while 2PL ensures data isn't corrupted by simultaneous edits, it is worth noting it doesn't entirely prevent deadlocks on its own, but it really is the foundational rule for transaction management. Okay, that wraps our section on transactions. Moving on to section 4, analytics, big data, and cloud. So now we're shifting gears from traditional relational structures into the modern era. We're talking exponential data growth, distributed computing, and the Internet of Things. Because let's face it, not all data fits neatly into rows and columns anymore. Traditional SQL relational databases remain the absolute best tool for day-to-day operational transactions, like processing a secure bank transfer. However, we now also have big data and NoSQL. The big data phenomenon is driven by massive volume, velocity, and variety of data coming from things like social media, sensors, and mobile devices. NoSQL, which actually stands for Not Only SQL, represents these newer distributed database architectures designed specifically to handle this massive, unstructured data. They prioritize extreme performance and scalability over strict traditional transaction consistency. To process this absolute ocean of information, we often turn to Hadoop. Now, it is vital to remember this. Hadoop is a framework. It is not a database itself. It allows us to process data in parallel across thousands of low-cost computer nodes. It relies on two main components. First is the Hadoop Distributed File System, or HDFS, which uses a highly fault-tolerant write-once, read-many model to store data blocks. And second is MapReduce, which is the programming interface that essentially breaks massive analytical jobs down, maps them to various nodes, and then reduces the output into a single cohesive result. And where on earth do we host all this? In the cloud, of course. When you look at real-world provisioning calculators for platforms like Microsoft Azure or Amazon Web Services, you can clearly see how cloud computing fundamentally changes software engineering. Instead of waiting months and spending massive capital to buy physical servers, an organization can deploy a fully functioning relational or NoSQL database in literally minutes using a pay-per-use model. You get software independence, massive scalability, and global reach, basically instantly. Section 5. Database administration. Of course, none of these incredible systems run themselves. In larger organizations, database management is divided up. First, you have the data administrator, or a DA. They are focused on strategic planning and policy across the entire company. They're managers, really, and their role is broad and entirely independent of any specific software. On the other hand, the database administrator, or DBA, is highly technical. They're the ones implementing the DA's policies on a day-to-day basis, managing the specific DBMS, like Oracle or SQL Server, and ensuring things like security, performance tuning, and backups. Knowing the exact difference between a DA and a DBA, or say being able to explain a left-out or join using the correct terminology, is vital vocabulary for job interviews. It proves to employers that you understand professional standards and corporate IT structures. And finally, Section 6, Capstones, Summary, and Themes. Okay, we've covered a ton of ground today. Let's synthesize all of this into our major themes. Here are the first two. Theme 1 is data modeling and design. By mastering concepts like entities, attributes, relationships, and normalization, you ensure structural integrity. Just remember the golden rule: bad design cannot be coded away. Theme 2 is the relational engine. This is all about how primary keys and foreign keys physically link the architecture together. They enforce referential integrity so that you don't end up with orphaned data, which allows you to seamlessly join tables and extract truly meaningful information. Moving on to our final two themes. Theme 3 is transaction management.
Think of this as the shield that protects your data. By understanding the ACID properties, atomicity, consistency, isolation, and durability, alongside concepts like deadlocks and the two-phase locking protocol, you know exactly how databases prevent absolute chaos when thousands of users connect and modify data all at once. And theme 4 is the future of data. Modern databases aren't just rows and columns anymore, they are distributed, schemaless, and heavily analytical. Concepts like big data, NoSQL, data warehouses, and cloud computing are the tools you will use to build highly scalable global applications going forward.
And that brings us to the end. The specific database software you use, whether it's an Oracle SQL Server today or some brand new graph database tomorrow, will inevitably change over the course of your career. But these foundational architectural principles, they are enduring. Knowing how to normalize a structure, enforce integrity, and manage concurrent transactions will anchor your entire software engineering career. So once again, huge congratulations on completing the program. Take this professional vocabulary, apply it in your interviews and your system designs, and go out there and build the incredible architectures of tomorrow. Thank you so much for joining me for this explainer.